Thank you, everyone, coming to the last day. And what I want to do today is sort of a mixture of some theory ideas and also some practical, but more, you don't have to do too much typing today, but just thinking practical. And we've looked at so far propositional logic and first order logic and type first order. Recall at type first order, we were playing this example about Jeff and Joe and the teacher when we were in the other classroom. And I think everybody saw the idea of typed first order logic. The benefit, same as in programming, if you have data types, you can find errors in your axioms more easily. And so now I just want to look at 2 or 3 more logics, but we won't do any examples, just to show you even more powerful logics if you want to say more complicated things about the world. We were having a nice conversation now. I have my students in Miami. I've given them a project to encode some of the rules of the US government. You know, we have the president, the Supreme Court, and the Congress, and there's rules. And they had to encode the rules and find out roughly, you know, when is the president lying? Is this the kind of things you want to prove? And so they used this logic for doing that. But now let's move up to something a little bit higher. Extended type first order. All right. And so this is the kind of thing when people are talking to each other. I'll say that Carlos said that his daughter is copying her homework. So I say that Carlos said that she said, and she said, no, my friend gave it to me. So you want to talk about statements that are true or false. Up to now, let's just go back. You might notice that we separate things that are true and false, like created equal, and objects in the world, John, A, F, and grade of function. So we separated objects in the world and true and false with separate things. And that it makes it a bit easier. Now we're going to bring these together so we can talk things that are true or false. We can say whether we can discuss, talk about things that are true or false. And that's when I say, Carlos said that she said that blah, blah, blah. So let's look at a nice simple example. And this is a famous example from a logician and philosopher, Raymond Smullyan. You might have heard of him. He has a wonderful book about logic. And the name of the book is, What is the name of this book? So it's a good title for a book. What is the name of this book? But so this is one of his little stories. So we have on this island 2 people, Mel and Zoe. And the people on the island are the knights, they are the good people, and the knaves, they are the bad people. All right. The good people always tell the truth, and the bad people always lie. They are liars. Always. Now, Zoe says, Mel is a knave. Mel is a bad person. This is what you do. You say, that man over there is a bad person. All right. And then Mel says, neither Zoe or I are neither of us are bad people. We are both good people. So something is funny here. Somebody is lying. And the question you want to check is, there's at least one good person and one bad person on the island. So Mel or Zoe, one is good, one is bad. We have to prove that. Can you prove that? I mean, if you think about it, can you prove? And which one? Is Mel a good person or is Mel a bad person? Is Zoe a good person or Zoe a bad person? Based on this, remember, Zoe says that Mel is a bad person, a knave, and Mel says we are both good people. Neither of us are bad. What is Mel? Is Mel a good person or a bad person? This is difficult. And this is what politicians rely on. They talk rubbish and you can't tell what the rubbish is because it's magically woven together. So now we can do something new. Let's look at this, how we would write this in TPTP World. We have people who live on the island, the inhabitants. We declare them as a data type, same as we did on Tuesday. Mel is an inhabitant of the island. Mel lives on the island. Zoe lives on the island. And then we have the is not. Is this person a good person? Is it a good person? Give it a person, it says true, false, good person, yes, no. Similarly, this is knave also says, take a person, is it a bad person? Yes, no. And finally, here's when we say, somebody says something, somebody says it, this is what they say. What they say is either true or false. And is it true or false that they said it even? So you notice now that we can have this data type $O on the inside as the argument of a predicate or a function. And that's an extra level of ability. So here we can see, we know that on the island, everybody is either a knight or a knave, good or bad person. So either for every inhabitant, either you're a good person, exclusive, or you are a bad person. All right. And now we know the good people tell the truth. So for all people, if you are a good person, and you say something, then it's true. Because not good people always say things that are true. And if you are a bad person and you say S, then it's not true because bad people tell lies. All right, that's it. And so now we know Zoe says that Mel is a knave. And Mel says Zoe is not a knave and Mel is not a knave. We want to prove there is one knight and one knave. There's somebody who is a knight and there's somebody who is a knave. So you can see here, it's a slightly more subtle logic. We can put this into E or vampire. It'll prove it. It's okay. But that gives you the ability to talk about things that are true or false, rather than only being true or false. You can talk about them being true or false. It gets a wrapped up version. All right. So there's something we could play with there if you're interested. Again, I just want to show you what these more powerful logics offer so you can model more subtle things. We can go to higher order logic. So higher order logic, for those people who like set theory, this is the perfect logic for discussing set theory and things like that. What we get now is more capability. In particular, we get lambda functions. And people, I hope, if you're not familiar with lambda functions, don't worry. It's just a way of writing a function in line, same as in Java. All right. And also, if you have a function that takes multiple arguments, you can just give it the first argument and not the second. If it takes two arguments, you've got a function, takes two arguments. You give it the first argument, but not the second. What happens? You get back another function, which takes only the one argument, the second one. So it's a subtle thing you can play on. I don't want to go into it because it gets crazy complicated. But what I want you to see here is also you can say things like, there exists a function that when you give it the argument 2, the answer is 4. There exists f such that f of 2 equals 4. What is the function f? There is some function, if you give it the argument 2, the result is 4. What function? Come on, easy. Suggest one. 2, squaring, huh? If the function is squaring, 2 squared is 4. What's another function that if you give it argument 2, the answer is 4? How about add 2? The add 2 function. So this, in higher order logic, you can find it. Please find me a function that has these properties. And that's very powerful capability in higher order logic. That means that the theorem provers, we go here, have to be more powerful. There's some examples here that show these ideas. And anything else I should say? So again, it's just more power as you go along. And so if you ever come in your life and you want to use logic to describe some part of the world, you can start with first order logic and you think, no, I need types. And you think, no, I need extended. And you have to keep trying until you find a logic that it has enough power to describe it. I think your stuff on Goldbach would be higher order as well, higher order logic. But now we're going to do something that's much more fun, is every logic we now have, we only have two, true or false. But true or false, not everything. Some things can be on the internet. It will tell you that Barack Obama is the president of the United States, and Barack Obama is not the president of the United States. So it tells you this Obama is president is true and it is false at the same time. Can things be true and false at the same time? Well, in reality, yes. We have data about the world where some fact is true and it is also false. And then you think, no, what do we do now? So we need to think about logics where we have more than just true and false. We're going to have logics that have, we're going to look at logics now that have three possible truth values: true, false, true and false. And you just allow that. You don't have a problem. You allow things to be both. We will look at a logic that has four values. It can be true, it can be false, it can be true and false, or it can be neither true nor false. It doesn't have a truth value. And that gives you more capability. Lukasevich, I think, depends which one, but yes, Lukasevich has a three-valued logic, I think, yeah. All right. So I just want to talk about, and I've showed you maybe this example before from the Walking Dead TV show. Everybody's watched The Walking Dead. You have to. This is part of university education, The Walking Dead. Okay. And you know that there are people who are alive. We think they are true. There are people who are dead. We think they are false. Then there's The Walking Dead. They are alive and they are dead. So they are true and false. And then there's people who are not in the show. They are neither. They're not true, dead, or alive. They just don't exist. So now we need a four-valued logic. So we have these glut logics. And this is what you were talking about. This is allow things to be the truth value both. You are both true and false at the same time. We have gap logics where you are neither true nor false. And that's the four-valued logic. And the version I use is FDE. But then we can also look at a three-valued logic. This is a simpler one, three-value. You have true, false, true, and false. So you can do paraconsistent logic, logic of paradoxes. And I think this is a beautiful statement. Contradiction is not a sign of falsity, nor the lack of contradiction a sign of truth. Contradiction is a normal thing. You have to think of it as a normal situation, so things can be both true and false. And that's not a contradiction, it's just normal. So here's a fun thing you can do with that. Let's take some examples. Now, so we know this is some logic. Here are the axioms, and here's the conjecture. We know in classical first-order logic, if we have the axiom Q, can we prove that P implies Q? If you know Q, does P imply Q? Well, yes, it does. All right, so we could do that. Yeah, I put it into there. If we know Q is the axiom, conjecture P implies Q, and we ask our friend E, let me just turn off the other one over here. Yeah, we know that if you know Q, then P implies Q. Sure, there it is, theorem. And that's normal. If you know Q, you know P implies Q. But now, if you move to the logic RM3, where things can be true and false, I'll run a theorem prover for RM3, one that I wrote some years ago, and we do this. Scroll down. There we go. Counter-satisfiable. So in a three-valued logic, if you have the axiom Q, you cannot prove P implies Q. Why is that the case? It's because Q can be both true and false at the same time. Before, if you have the axiom Q like this, that means Q is definitely true. But now it means it's true, or maybe true and false at the same time, because we allow that in a three-valued logic. And this sort of logic, and the other one with four values, is used when you want to look at properties of operating systems. The operating system of a computer, Linux or Windows, you have to know the properties of what's going on because you rely on it. When you are working every day, you rely. You think Windows just will work. No, you don't. Windows is... If you have Linux, you think it will definitely work. It's reliable and it works. Why is it reliable? Because you can look at what's happening inside in the data structures and model it in a logic. And you often need a 3 or 4 valued logic because operating system state can be contradictory like that. So you have to allow for a contradictory state when you want to check how all your processes are running inside your computer. This was used by the military in Australia. So, you know, it was in helicopters, and helicopters in the army have computers on them, huh? And they run Linux, seriously. And the computers control the guns and the engines and everything. It's all done. And so you have to make sure that the operating system is perfect, because you cannot have your operating system go wrong when you're fighting on a helicopter. It has to be correct. And so the Australian government paid people at Australia National University to build a version of Linux where they checked everything right down. So now when that helicopter takes off, they know that the Linux, it's a simple Linux, not Ubuntu, it's a smaller one, it's cut down, is definitely safe. It won't ever crash. It will always control the guns correctly and things like that. Great work by Gerwin Klein. It's the guy who did it. And they used other things as well. So this is kind of, let's look at another example. Remember what we did when we did classical logic. We said our axioms must be consistent. Well, here we have inconsistent axioms. And I've told you, if you have inconsistent axioms, you can prove anything. So if I know P and not P, I can prove Q. Sure, this is classical logic. In three-valued logic, you cannot prove it. So because three-valued logic allows things P to be both true and false at the same time. So that is not a contradiction in three-valued logic. It's okay, it's acceptable. P and not P, quite happy. And there's several other differences like that. For people who are interested in set theory, you might know the axiom of separation, if you're into mathematics, all right, which says there is no universal set. There is no set that contains everything, all right? And so you can, in classical logic, you can prove there is no universal set. In three-valued logic, you cannot prove it because you can have sets that contain themselves. You can have a set that contains an element and also does not contain the element at the same time. It's like Schrodinger's cat. You know, you don't know if the cat is dead yet. You can have that. That's another example. So if you want to do quantum physics, you need this kind of logic, right? Because quantum things can be in two states simultaneously. So that's another nice application. So then that's what I wanted to sort of put that dot in here, but I haven't. So then the next one we should look at is non-classical logics. So again, this is dealing with different types of truth. Up to now, things are definitely true or definitely false, or in multi-value, definitely true and false. But let's just go back to two-valued logics where things are true or false. But sometimes in the world, you don't know for definite that something is true or false. And so we want to move on and we'll look at modal logics. Modal logics, you can say something is possibly true. It's possible that I will drink beer tonight, but it's not true because we don't know. Or maybe it's necessary that I drink beer tonight. So we talk about something being possibly true or necessary that it's true. And that's a way that you can talk about the world. The proof of the existence of God that I mentioned, the proof was it is necessary that God exists. That's what's proved. It didn't prove God exists. It actually proved it is necessary that God exists. And that's a different kind of thing, different thing you want to talk about. And so there's many, many, many of these logics. We can talk about modal logic, I've just mentioned, alectic modal, where things are possibly true or necessarily true. So you've got three states. And then we can talk about epistemic logics, where you talk about knowledge. I know that it's true, all right? So it's talking about knowledge of truth, which is important because you might say, you know that tomorrow is Saturday, but maybe somebody else doesn't know. So you can talk about truth with respect to an agent. So if you're in a multi-agent system in artificial intelligence, where you have many agents, you can talk about the agent knows it's true. Sorry, that link is dead. What else can we talk about? We can talk about deontic logics, where deontic logics, I think I've got, deontic logic things are forbidden. So deontic logics is good for law, because in law it says it is forbidden to drive when you are drinking beer. All right. So you want this notion of forbidden, and you want to say it's obligatory. It is required. It is required to have a license before you drive your motor car. And so for law, you often need to use that sort of construction. And these modal logics are, I see as the future. In the TPTP, we've only had it for 2 years now. It's kind of new and exciting, and we're working on it. So here's a little example in alectic modal. If there is some product, some software that a person works on, he's programming very hard. Let's put this, wait, let me also do this in Spanish for you. English, Spanish. Hold on, I'll just put it up so you can read it in both languages. I think that helps. Okay, so now I have the Spanish version. That's easier for everybody. It's better, eh? All right. So if it's some software and your person is working hard late at night programming, then it is possible. It's possible. It's possible that the person will get richer, make lots of money from working hard. It's not necessary. Sometimes you work very hard and you make no money. All right, that's okay. That's when you study sociology. All right, you work very hard and you make no money. Good summary in a mathematics class. Yeah. Yeah. All right. So this is one axiom. If you work hard, it's possible that you will get rich. All right. But nobody necessarily gets rich. Sometimes you work hard and nothing happens. So my two friends, Alex and Chris, they work very hard on their theorem prover, their ATP system called Leo 3. So now I want to prove it's possible that Alex gets rich, but it's also possible that Chris does not get rich. So I go to them and say, well, Chris, it's possible you will not get rich. Alex, it's possible you will get rich. And he needs to because he has a new baby. All right. So how do we write this all down? First, we'll look at how it's written in a book of logic. And maybe you have come across this. We have to look in English because it doesn't translate. The box operator means necessary, and the diamond operator means possible. So in this, what do we have? We have the people who are programmers, the product, the software. Alex and Chris are people. Their theorem prover, Leo, is their product. Works hard. We send in a person and a product, and it returns true. So we say works hard, Alex, Leo is true or false if he doesn't. And gets rich, we send a person and it turns true or false. So here we see it written in logic. For every person or P, there is some, if there is a product and P works hard, then it's possible that P will get rich. So the diamond is possible. Yeah? Similarly, there is no person, that is not the case, there is no person who is necessary that they get rich. Nobody will definitely get rich. It's not necessary. Alex and Chris work hard on Leo, and now we want to prove it's possible that Alex gets rich, and it's possible that Chris does not get rich. So then now we need more TPTP syntax. Just ignoring the top, here's how we write this possible. Possible at, and then you put it in brackets, get rich. It's a little bit clunky, but we needed that for more things. It's necessary that P gets rich. The conjecture. It's possible that Alex gets rich, and it's possible that not Chris gets rich. I want to point you out to this at the top here. This is an extra thing that is necessary, that you have to have when you're dealing with these non-classical logics, because the syntax, how you write the program, how you write your axioms, how you write the conjecture, you can use the same language for many different logics. This is modal, deontic logic, epistemic logic, all of them use the same. So you have to tell your theorem prover, your ATP system, you have to tell the ATP system, which logic please use this logic. So here we're saying we're using a modal logic and some information about the logic. This is a whole semester or 2 semesters of study about logics. But all you need to know here in this logic, we are just saying, this is the logic that we want to use for this particular problem. And so I can grab all of this in the usual way, and we can check the syntax. But notice I don't have a check for satisfiability because there is no tool for this yet. Right, there's no program that can check for satisfiability of this that I know. So we go off into proving it. And if you want to prove for these logics, there's only one prover really of any use. It's Leo, the Leo project. Leo prover. He can do Leo 3 prover, not Leo 2, Leo 3 prover. Boop. And he will do the proof for you. Grinding, quite a lot of work. Whoa, it looks horrible, but yes, he finds a proof. How does it do it? This is a complicated logic. So what Leo does, he takes the problem, this, and he does a translation to higher order logic, the one I mentioned just now. He can take, there's a translation process. And that translation process, you then have an equivalent higher order problem, which you can then give to a higher order theorem prover. And we have 3 of those. We have Vampire, E, Leo, and lots Z3, many higher order provers. So we take modal logic, translation to higher order, its equivalent higher order, then we give to a higher order ATP system. Yeah.
The semantics in the modern logic in PPT are
it's good. No. Yeah. Good. Yeah. Okay. Well, in this, what we have said here, we're using M, huh? So you know the. Hold on. I know what you need to know. Okay, let me make that bit bigger. Right, so these are all the different modal logics. You know the modal cube? The simplest one is K. Most powerful one is S5. So for that problem, I'm using the M logic over here. So it's weaker than S4. Yeah. So that's why I say you can study modal logic for a whole year and just learn a little bit about it. It's complicated. But you're correct. So we have to say which logic, and you might, as I did in my example over here, I said I'm using M, system M. It's a little bit weaker as a logic. All right. So I think that's very nice. So I think everybody should try and code this problem. And there it is in English. And I'll put it up in Spanish as well. Let's spend 10 minutes, everybody trying to do that problem. Let me just get everything together here. All right, everybody try. Everybody did topology exam yesterday. And the exam was unfair. What's the answer? I don't know the answer to this. Wow, this is quite hard. Try it, try it. I'm giving you some clues up over here so you can get it done. Oh, we need unfair. You need to see more. I don't know the answer here. I'm trying to work it out. Mm. All right, I don't know if that works. That's my answer, but I don't know if it's correct. Maybe you quite welcome to disagree. I'm wrong. When I'm teaching, that's what I say. The students at the back say, please speak loudly, we can't hear you. And I say, no, I have a volume control. And I can show you, and I go to the students. Yeah, it works. Oh, I had here I put at, oops, sorry. Here I put at instead of dollar. It should be dollar. Then it works. My answer for it. Right, we'll just do 5 more minutes of people trying it in. You there yet? You always shout first. I'm ready. Carlos, you see what I did it the other way around. I put the for all students, it's necessary that it's unfair. But you said it's necessary that for all students it's unfair. And that means something different. This worked, I just got a proof, so I'm happy. But yours, I think it might work as well. It's fine. All right, stop because I know this is hard. Struggling. All right, so let's just go through it, and you can see what I've done is how you can write these sorts of subtle arguments. And this is the kind of thing you need for law as well. So I've said for all students, it's possible that there is some exam that is unfair. Hey, back row, silence. Here's something to throw. Chatting. All right, so you can see the use of the possible operator there. I'm saying for all students, it's possible that there exists an exam such that the exam is unfair for the student. Similarly here, I'm saying for all exams, if there is some student who cheats, then for all students, it is necessary that it's unfair. And I think that probably needs a bracket around it like that. No, it doesn't. All right, Donald is cheating. Therefore, we want to prove it's possible that there is some exam that is unfair to Alex. And you can see suddenly Alex never been spoken about before. Now we can conclude because Donald cheats, something is unfair for Alex. Okay, so let me just go back to my notes and just round up what we've done this week, just to give you a feeling of what's going on and where you might go next if you're interested in this. So we looked on Monday just at the general ideas. What is automated theorem proving? What can you do with it? What examples of applications have we looked at? And we looked at the TPTP language that you've been using Tuesday, Wednesday, and today. Then on Tuesday, we looked at propositional logic. The horse races are fixed. Things like that. Remember, we looked at that example. And we looked at first order logic about Maggie and Bob. So stronger logic. Then that was on Tuesday. and Wednesday, yep, we did more of this, and we did the type logic where you have data types, such like programming. And on Thursday, we looked at the structure. We looked at resolution, clause normal form. What is the general internals? And I pointed you at the PyRes prover if you ever want to play with it and make your own and think you can make a better one. And so then today, my idea was, and I know it's getting complicated and difficult now, just to look at these strange logics. But it's important to know maybe you can't do it but to know that the logics exist. And so that when you come out, if you're going to work in industry and you work using reasoning tools, you think, hell, I need to go and read a book about modal logic. I remember that from Jeff telling me, and it was horrible. But, but at least you know that it exists and you can go and find it, because if you don't know it exists, it doesn't. You also saw today the multi-valued logics, because the world is naturally a contradiction. When we looked at these logics here, we said, first thing we do, check the axioms are consistent. And when you go to reality, the world has contradictions. And if you cannot remove the contradictions in the world, you have to deal with them. So you can use a multi-valued logic for that. And then you've got the tools, you've seen it. Again, I encourage you to play with this as much as you want. I've got plenty of compute power available. And my email is, of course, a very easy one to remember. If you haven't got it, but you can always email me. It's jeff@tptp.org. All right. And then that will get to me. And I can answer any questions if you want to use this, if you want to play with it, things like that. I'm sort of been talking to people about setting up some projects between UNAL and my university for people to do the master's level working in this area. I don't have any money at the moment to pay people to come to Miami. I'm down to my last 18,000, which in Miami is no money. To die on that, it's less than half a month or something. But we could certainly do some work together if people are interested, a lot of opportunities. But I am grateful you came. And so I bought special prizes for the people who made it. And, yeah.
Universidad Nacional de Colombia, proyecto cultural, científico y colectivo de Nación.